Hi, it's me, Dr. Prasad Puthiyillam, with the class series Organic Chemistry, class number 4, Electronic Effects and its Applications in Organic Compounds. So, electronic effects in previous classes, I explained about the resonance and mesomeric effect, even the difference between resonance and mesomeric effect. Both are almost the same, but a small variation that is due to the that direction. Based on the direction, we classify in the resonance or mesomeric. Then hyperconjugation effect, inductive effect, as well as electromeric effect. So electromeric effect, that is, will not consider much in case of arrangement of electrons. Only in presence of an attacking reagent that electromeric effect comes into play. Therefore, if you consider a molecule, organic molecule, which having both all these three types of possible electronic effects, then we always have to give a first preference to resonance or mesomeric effect, and second preference is given to hypoconjugation, and third preference is given to inductive effect, because the resonance or mesomeric effect, that is a distant independent effect, whereas the inductive effect is distant dependent effect. Only up to third carbon atom or third molecule the effect will be there. And hyperconjugation is in between that of mesomeric as well as inductive effect. Therefore, this is the way how we identify the or give the preference to the electronic effects in organic molecules to explain their stability or reactivity or stability of intermediate. So relative stability of reaction intermediate, if you discuss carbocation, so one of the intermediate formed during writing the chemical organic reactions, the electron movements towards carbon carrying the positive charge will always stabilize the carbon with the positive charges. Therefore, this example, that is from methanol, one hydrogen is lost or it having a positive charge. So the oxygen will be giving the electron, oxygen this will be sharing the electron with the p orbital with no electron. Therefore, this is the type of mesomeric effect. And even oxygen compared to hydrogen, electron is high. Therefore, this OH bond also will be shifting towards oxygen. Therefore, somewhat we can explain about the stability of this carbocation. Compared to the ether or alkoxy group connected to that carbon with positive charge, previous case here we seen that is hydrogen, that is comparative to oxygen, that is more electropositive one. Therefore, if you replace it with alkyl group, then the stability of that carbocation will be less. Therefore, the electron donation by R is comparatively less in case of compared to that of H. So there we can think about the inductive effect also. Then comes the conjugated systems. So here positive charge carbon and the conjugate position, that is a double bond. So this double bond can shift. Therefore, this is the resonance structure, the resonance stabilization. The first two cases, that is mesomeric stabilization, that is unidirectional. Therefore, the mesomeric effect is more important than that of the resonance to explain the stability. So here the resonance, this double bond will shift here and positive charge will be moving to the third carbon atom. Or if you think in the reverse direction, the positive charge will be shifting 1 to 3 with the double bond. Then comes the tertiary butyl group or alkyl substitution. More alkyl substituted molecule with of the carbon substituted to carbon carrying positive charge will stabilize. It can have both inductive effect and hyperconjugation, but hyperconjugation is more stronger. Therefore, here these three hydrogens can form hyperconjugated structure, formation of double bond here, positive charge shifting to that hydrogen with that hydrogen. Like that, here three each on a carbon atom. Therefore, total nine hydrogen atoms are there, which can form hyperconjugating a structure, and three methyl group will also contribute to as the inductive effect. So both inductive effect and hyperconjugation is there, but hyperconjugation is having more preference. Then comes the di-substituted molecule. So dimethyl substituted carbocation. So two methyl groups are there. Therefore, here number of hyperconjugating possible hyperconjugating structures are less. Therefore, I can say its stability will be less. Then comes mono-substituted cases. Therefore, positive charge will be the stabilization of positive charge will be comparatively less. Then comes to CH3 plus. So this is just an order that I took an example to explain it. I can have more examples to explain the stability of carbocations. Then carbon with a free radical. Carbon with a free radical, that is in the case of homolytic fission cases, the carbon may get a free radical. So it is as that of carbon with a positive charge. More number of alkyl substitution, more hyperconjugating structures are possible here. Therefore, that is more stable compared to the other di-substituted or monosubstituted or without any alkyl substituted cases. Then carbanions, carbon with a negative charge. So carbon with negative charge, electron movement towards the carbon carrying negative charge actually destabilizes. So this is the case as reverse that of carbocations. Therefore, try the tertiary butyl group with a negative charge will be less stable, and the one with a negative charge, that methyl anion, will be more stable comparatively. So more examples you can take, and you can think about the possible hyperconjugating structures or even the inductive effect. So here are all cases inductive effect is also there, but hyperconjugating effect we consider or give more preference. Then if you think about then it comes the conjugated structures. Here the negative charge can form double bond here. Therefore this double bond will break towards the carbon will get negative charge. So this is a resonance stabilization. Therefore resonance stabilization gives more importance than that of a hypoconjugation. Then if it contains a phenyl group attached to that, phenyl group means a benzene, alternate singular double bonded in a cyclohexane molecule, then we call it as benzene or phenyl group. So if phenyl group is the phenyl group have the capacity to withdraw this electron to the resonance. Therefore, comparatively to the aliphatic cases, so the aromatic cases how more stable the carbon carrying negative charge, if it is connected to a aromatic compound, it will be more stable. So we can list on so diphenyl substituted, triphenyl substituted cases you can discuss, and even carbon with carbon carrying negative charge, but and it is also having a triple bond with the next carbon, that also will be stable. There is no electron movement, that is explained with the hybridization, sp hybridization. So one other example which is given here, that is cyclopentadienyl anion. Cyclopentadienyl anion, here also the resonance stabilization is strong. So the electron here, it can form a double bond here. Therefore, the next double bond, this double bond will shift or move towards the carbon, and further it continues giving a double bond, and the next double bond breaks towards the carbon of the corner, carbon atom. Therefore, the cyclopentadiene anion is also stable. Therefore, stability of carbocations, carbon with free radical, carbanions can be explained with the electronic effect. Therefore, we can predict which compound will be the intermediate, possible intermediate, and what will be the product of that reaction. Then next is stability of alkenes. Stability of alkenes can also be explained. Say if the alkenes means doubly bonded organic molecule, or carbon-carbon double bond is there, we call it as alkenes. If it is a conjugated system, then conjugated system will there is a free movement of the electron is possible. Therefore, the double bonds are more stable, or formation of the double bond in conjugated system is more stable. And if more alkyl substitution is there, then that alkyl substitution, due to the inductive effect, the electron density will be towards the carbon carrying that double bond, that also will be stabilizing. And if steric hindrance is there, then the steric hindrance also will affect the stability. And without any substituted cases, there is no nothing to support the doubly bonded the formation of double bond. Therefore that cases are discussed less. Therefore we can say even steric hindrance is there or not, electronic effects are more preference, we have to give more preference than steric hindrance to explain the stability. So the first one, that is the case of a conjugated system. So the pi bond shifting, it is possible, or the electrons are free to move. Therefore this system, it is more stable than that of the say completely substituted case, a carbon carbon double bond with all alkyl substitution. It will be contributing the electrons will be contributing toward that. Therefore the stability is more. Then comes the next tri-alkyl substituted case, trimethyl substituted case there. Therefore, the number of substitution is decreasing, then stability is decreasing. Okay, again the number of substitution it is decreased, the corresponding stability is decreasing accordingly. So here this is a case, two cases I can give here. So the first case that is trans case, and the next case that is cis case. So here due to the steric hindrance, the CH3 groups are on the same side of the double bond, that creates a steric hindrance. Whereas same two substitution, but the alkyl methyl group, CH3 group are on opposite side. There is no much steric hindrance. Therefore, steric hindrance also we will consider after electromeric effect. Electronic effects. Then comes the monosubstituted and without substitution. Therefore, the stability of alkenes in the more conjugated systems are more stable, and alkyl substituted cases are also stable, and less hindrance is there, then also it is stable. Then acidic nature of molecule, the relative acidic strength can also be explained, because we know acidity is the how we measure in case of organic compound, it is the ability to give the proton H plus. So if H plus goes, means the remaining structure should be stable. Then we can say that that will be more acidic in nature. Say example, if you take this is hydroxyl group connected to a cyclohexane molecule or cyclohexanol. So cyclohexanol, it is not acidic in nature, because the hydrogen cannot move, cannot become H plus so easily. Whereas if you take the case of corresponding aromatic nature, aromatic molecule, that is phenol. Phenol, it can be, it is acidic in nature actually. Therefore, it can form H plus separation is possible, because when H plus is when a hydrogen goes as proton H plus, the remaining structure, that electron density, it has to be stabilized. Then only the free movement of free H plus will be free, or we can say it will be acidic. The electron here, it can form resonance with the conjugated system, that is the benzene molecule. Conjugation is there, that is the lone pair atom with a lone pair, then next atom is connected to a double bond. Therefore, this is conjugated system. The conjugation is possible. So electron movement is possible like this. That movement of electrons that is explained in previous class. Therefore, I am not going in detail here. So representing it as such. Therefore, carbon oxygen double bond is formed, and the ortho and para positions are comparatively getting more electron density. Therefore, phenol is acidic in nature. And the reactivity of the molecule phenol can also be explained with the same resonance structure. The ortho and para positions. So here two ortho position. These two are ortho position, and the last one, that is para position. So towards the electrophile, the reaction towards an electrophile can be explained with that of resonance stabilization. So electrophile is one which is having a positive charge, or it is the electron seeking molecules. So it can when it comes to reactor, it can attack the two ortho as well as the one para position. Therefore, the reactivity can be explained in case of with the resonance stabilization or any electronic effect. So in case of a carboxylate ion, so carboxylic acid, carboxylate ion actually it is electron pulling effect. So it takes the electron density from the benzene molecule. Therefore, as comparatively, the ortho and para positions are having slight positive charge, means less electron density compared to the meta positions. Therefore, if an electrophile E plus trying to react with the carboxylate ion, carboxylic acid molecule, it prefers to combine with the carbon which is in meta position, not ortho and para. Therefore, this is meta directing group. And even reactivity of methyl benzene can also be explained. Methyl benzene, it has got the methyl group has got three hydrogen. These three hydrogens are in conjugation with the system aromatic system. It can form hydrogen hyperconjugating structures. Three hyperconjugating structures are possible, continued with the benzene ring molecule. Therefore, it can be represented like this. The ortho and para positions are having more electron density, and this gives the electrophile to attack the ortho and para position. So that about the organic molecules, their stability or the reactivity with that of electronic effect. Hope you understood this concept. Thank you very much for watching my video and have a nice day.